I am Dr. D.K. Tripathi, Assistant Professor of Physics under the Department of Basic Science and Humanities. Let us have the concept of crystal planes or lattice planes. The lattice points forming a space lattice may be thought of as occupying various sets of parallel planes. Some examples of dividing a lattice into such sets of planes are indicated in the adjacent diagram. With reference to the direction of the basis vectors, each set of planes has a particular orientation, which you can view here, that can be determined by any 3 points of a plane, provided the points are not collinear. In each of the points lies on the crystal axis. The plane may be specified by giving the position of the points along the axis in terms of lattice constants. If suppose, for example, the atom determining the plane have coordinates 4, 0, 0 or 0, 1, 0 or 0, 0, 2 relative to the basis vector from some origin, the plane may be specified by 3 numbers 4, 1, 2. But it is more useful and universal for crystal structure analysis to specify the orientation of a plane by some another set of 3 numbers, which we will have the introduction later on. Now, second is crystallographic direction. Before going to the very important concept of Miller indices, let us have the concept of crystallographic direction. In a crystal, the concentration of atoms in different direction is different. We all know that. Because of that, the anisotropy of the crystal is seen. So, planes for crystallographic analysis is always required. Now, as given in the video, the crystallographic direction in a crystal is defined as the line joining any 2 points in the lattice. In 2 dimensions, the crystallographic direction is expressed as a line passing through a point AXY as shown in the diagram, and any other lattice point taken as the origin 0. Actually, origin is O 0 0. Now the coordinates x and y being whole number. In 3 dimensions, the crystallographic direction of any point A having coordinates x, y, z, where x, y, z are whole numbers, is conventionally denoted by putting x, y, z in brackets. So the crystallographic directions of the as shown in the diagram will be given by A100. Representation of crystallographic directions in 3 dimensions. Just we discussed that conventionally the directions are denoted by 3 letters by putting them in the brackets as x, y, z. Now, in the figure we are having a cube. Let us try to write down its unit cube. We have taken the unit cube, and let us try to write down the directions or crystallographic directions of the corner points of the unit cube. So how it can be written? You see, go to the point Q. You will find that Q is written as 101, whereas the point P is written as 001. Point S is written as 011. So like that, there is a table which summarizes the points and the directions. Point A is 100, direction is 100. Point B is 110 and direction is 110. So like that we can represent the directions of any two-dimensional or three-dimensional geometrical objects using the crystallographic direction. So crystallographic directions are very important in the case of solid state physics. Without them we cannot proceed or we cannot denote anything. Miller discovered a method to designate a plane in a crystal using three numbers H, K and L, which are known as after him Miller indices. Miller indices can be defined as the three smallest possible integers which have the same ratios as the reciprocals of the intercepts of the plane concerned on the three axes. So there are some rules following which we use to calculate the Miller indices of a lattice plane. At first, we will have to find out the intercept of the plane on the three crystal axes OX, OY, OZ. Let these be PA, QB and RC, where A, B, C are the corresponding primitives and P, Q, R are the intercepts along the direction A, B and C respectively. Now, if you take the reciprocals of the numbers P, Q, R, then this will be equal to 1 by P, 1 by Q and 1 by R. Now, later on we will have to find the smallest possible integers H, K, L by multiplying the reciprocals by the LCM of P, Q, R, such that H ratio K ratio L is equal to 1 by P ratio 1 by Q ratio 1 by R. Now the numbers HKL are the Miller indices and the corresponding lattice plane is represented by HKL. So we will discuss later on in the illustrations that how we can find out the Miller indices. As I told you earlier that theory is always confirmed with the help of the numericals. So just to have the strengthened idea about the Miller indices, which is very fundamental and very important concept in crystallography, we are going to solve some numerical problems. These numerical problems which we are going to solve are very basic problems. The advanced problems will be solved in the classroom, but just for understanding we are going to solve that. So the first problem is that in a crystal a lattice plane cuts intercepts of 2A, 3B and 6C along the three axes, where A, B and C are primitive vectors of the unit cell. Determine the Miller indices of the given plane. Now here if we take PA, QB and RC as discussed in the theory be respectively the intercepts of the plane on the three crystal axes, then we can write PA ratio QB ratio RC is equal to 2A ratio 3B ratio 6C. So from that ABC will be cancelled out and we will get P ratio Q ratio R is equal to 2 ratio 3 ratio 6. Now taking the reciprocals of them, we will get 1 by P ratio 1 by Q ratio 1 by R is equal to 1 by 2 ratio 1 by 3 ratio 1 by 6. So the Miller indices will be 3 to 1. Let us take a typical problem. As in the last problem we have taken that the intercepts are whole number. There may be the intercepts which are not in whole number, but Miller indices are to be in whole number. So how to find that? Because in the concept of Miller indices I told you that these are whole numbers. So if intercepts are not a whole number, how Miller indices will be whole number? Let us try to understand that. So for that, let us take an example. In an orthorhombic crystal, a plane makes intercepts 2.93 millimeter, 4.47 millimeter and 2.35 millimeter along the three crystallographic axes. The corresponding primitives being 3.05 angstrom, 6.99 angstrom and 4.90 angstrom. Deduce the Miller indices of the cleavage plane. So we will have to find out the Miller indices. What we come to know, that we will take this as P into A ratio Q into B ratio R into C. So here in place of A there is 3.05, so we will multiply this, and because of that we will get 3.05 P ratio 6.99 Q ratio 4.90 R is equal to 2.93 ratio 4.47 ratio 2.35. Now if we bring all the numerals in the right hand side, then we will get P ratio Q ratio R is equal to 2.93 by 3.05, ratio 4.47 by 6.99, ratio 2.35 by 4.90. So from that we will get, after simplification, 0.96 ratio 0.64 ratio 0.48, and these are in the ratio 6 ratio 4 ratio 3. Now taking the reciprocals, 1 by P ratio 1 by Q ratio 1 by R is equal to 1 by 6 ratio 1 by 4 ratio 1 by 3. So we will get the Miller indices of the plane as 2, 3, 4. Let us discuss Miller indices in some more details. Any plane parallel to one of the coordinate axes has intercept of infinity and index 0 for that axis. Miller indices define a set of parallel planes and not a particular plane. This is always to be kept in mind, that it defines a set of parallel planes, never a particular plane. All equally spaced parallel planes have the same index number, that is Miller indices HKL. When the intercepts of a plane on any axis is negative, a bar is put on the corresponding Miller indices. If the intercept is negative, we will have to put a bar. We cannot write minus. If a plane passes through the origin, it is defined in terms of parallel plane having non-zero intercept, because it is passing from the origin, so it is having non-zero intercept. The complete set of crystallographic equivalent directions of HKL is a member and is expressed by enclosing the direction indices in a single bracket, as we have shown earlier, HKL. Interplanar spacing. As the name suggests, here we will find the distance between the two planes. For this, if we take a family of parallel planes HKL, the spacing D or DHKL between the adjacent planes of this family can be calculated by taking any lattice point as an origin, erecting coordinate axes in the three crystallographic directions A, B and C, and finding the perpendicular distance between these origin and the plane which is nearest to the origin. Then the plane would be A by H, B by K and C by L as intercept on the ABC axis respectively. So here, if intercepts of the HKL plane on ABC axis are respectively A by H, B by K and C by L, which is shown in the figure, then from figure we can write DHKL is equal to OP. This is equal to A by H cos alpha. That will also be equal to B by K cos beta. That will be equal to C by L cos gamma, where alpha, beta and gamma are the angles between the normal to the plane and the A, B and C axis respectively. We should take in mind that alpha, beta and gamma are the angles between the normal to the plane and the crystallographic directions A, B and C respectively. If n cap is the unit vector normal to the plane, then we can write n dot A, that can be written as A cos alpha, n dot B will be equal to B cos beta, n dot C equal to C cos gamma. Now DHKL will be equal to n dot A by H, which will be equal to n dot B by K, which will be equal to n dot C by L. So let us call this as equation number 2. Now in any orthogonal lattice, if we take XYZ axis along the crystallographic directions A, B, C respectively, then equation for HKL plane having the intercepts A by H, B by K and C by L will be written as X by H, which we will discuss later on, just later on. So we can write X by A by H is equal to Y by B by K is equal to Z by C by L equal to 1. So this H will go in the numerator and multiplied by X, K will go to the numerator and multiplied by Y, L will also go to the numerator and multiplied by C. Due to that we will get Hx by A plus Ky by B plus Lz by C is equal to 1. Now if this is, then let us take this as phi. So phi is function of xyz equal to 1. Let us call this as equation number 3. Now what we know that del phi can be written as magnitude of del phi into unit normal vector n. So from that the magnitude of del phi can be found as magnitude of del phi will be equal to under root h by a square plus k by b square plus l by c square. Now the value of unit normal vector n will be equal to del phi by magnitude of del phi. We know that this del phi can be written with the vector ijk. So we will write this as I h by a plus j k by b plus k l by c, and the value of magnitude of this del phi is under root h by a square plus k by b square plus l by c square. Now from equation number 1 was dhkl is equal to a by h cos alpha, b by k cos beta equal to c by l cos gamma. So from equation number 1 we can write dhkl is equal to normal vector n, unit normal vector n into vector a by h. So from that if we take 1 by h outside the bracket and put the value of unit normal vector n, and a is multiplied and that a is written as unit vector I into a. We know that vector a can be written as magnitude of a into normal unit vector I. So that we have used the concept here and written. So because of that this will be written as dhkl is equal to 1 by under root h by a square plus k by b square plus l by c square. Now if in any cubic system a is equal to b equal to c, then A, B and C, in place of A, B, C, all will be replaced by A. A will be A and B will be replaced by A and C will also be replaced by A. So this A will come outside the under root and will go to the numerator, and because of that we will get the interplanar spacing between any corresponding planes is equal to DHKL is equal to A by under root H square K square L square. Now just take in mind that H, K and L are Miller indices. So with the help of Miller indices we can find out the distance between the planes, or interplanar spacing can be determined using the Miller indices and lattice constant A. These are some of the references which you must pursue to know more about the topics. Thank you.